Alright, so in this chapter we're going to look at the difference of two means. So what we have is we have an applet here, and I can show the difference between two normal distributions. Okay, so I have the red distribution and I have the black distribution. Okay, and what we're doing is we're taking samples here. This is the sample distribution. So you notice that our samples n1 equals n2, which is 2, so our sample sizes are 2. And of course we know if we increase sample size, our sample distribution variation decreases. When sample size goes up, variation goes down. Okay? So where these are this black distribution. The population distribution is centered at 5, and the red distribution is centered at about 9. And then the sample distribution comes down here if we did samples of size 2. So if we took 2 from each distribution and found the mean and plotted it, then this is what our two distributions would look like. Well, we know whatever the mean of our population is, then the mean of our sample distribution is going to be approximately the same. Okay. And what we did down here in this bottom one, okay, is we subtracted the red distribution minus the black distribution. So we get a difference of here, this is the difference of the mean, we get a difference of approximately 4. And that's because the red has a mean of 9 and the black has a mean of 5. So the mean difference would be approximately 4. Okay. And to no surprise, our population distribution was normally distributed, and our for both distributions. And we know if our sample sizes are large enough, though we have very small samples here, our sample distributions will also be unimodal and symmetric, and we would consider that to be normally distributed. Well, if our sample distributions, both of them, are normally distributed, then what happens is the difference of the two means distribution, this one on the bottom, is also normally distributed. So as long as this in here, we know that this is normally distributed, then we know that the difference is also going to be normally distributed. And based on that, that's going to allow us to use normal models to do the inference for the difference of two means or two proportions, which we're going to do in this chapter. Okay, so we're looking at two proportion hypothesis test now. So a two sample hypothesis test is a test to compare two parameters, where we're really looking at the difference. A hypothesis test is testing if there is a difference, and a confidence interval is trying to estimate the difference between the two parameters. Okay. Alright, so let's look at example 1 here. Would being part of a support group that meets regularly help people who are wearing the nicotine patch actually quit smoking? County Health Department tries an experiment using several hundred volunteers who are planning to use the patch to help them quit smoking. The subjects were randomly divided into two groups. People in group 1 were given the patch and attended weekly discussion groups. With counselors and others trying to quit, people in group 2 also used the patch but did not participate in counseling groups. Okay. After 6 months, 46 of the 143 smokers in group 1 and 30 of the 151 smokers in group 2 had successfully stopped smoking. So these results suggest that support groups could be an effective way to help people stop smoking. Is there evidence that a support group helps people to quit smoking? Okay, so In this problem, we're comparing two proportions. Now, when I write my parameters, I like them to be fairly descriptive. So you could write them p sub 1 and p sub 2 for p sub group 1 and p sub group 2. But what I'm comparing here is people who took part in the support group versus people who did not do the support group. Okay, so this I would probably label as P sub B, and B would stand for both. So this is the proportion of people who quit smoking using the patch and the support group. And then I would probably label this P sub P, and this is the proportion of people who quit smoking using only the patch. Okay, so they only used the patch, but they didn't have the support group. So my hypothesis, my null hypothesis, is that they are equal. There is no difference. My alternative hypothesis is I want to see that the support group helped more people quit smoking. So that would be the people who did both. So I'm going to do P sub B is greater than P sub P. Is there evidence that the support group helped? Or do you just only do the patch and you don't need the support group? Okay. So that could be good for business too, because if you're the manufacturer of the patch and that's all you need to quit smoking, you don't need anything else, that could be good for business. Okay, so our assumptions and conditions are, we have three that have to do with the sample. Now these right here, these samples were randomly selected. I'm going to put this in kind of a narrative format. You could just list them if you want. The samples are independent, not the people. When you're comparing samples, it must be the samples that are independent. Okay? We got 143 smokers here and 151 smokers there. So 143 and 151 are both less than 10% of all smokers. Now we looked at that applet to start this chapter, and we said if the sampling distribution of two means is normally distributed, then the difference of those two distributions will also be normally distributed. So we have to check that both of these sampling distributions will be normally distributed. So we got to do NP hat sub B. Now, how many people successfully quit smoking in the in the group that had the support group? Well, 46 of them did, and that's greater than 10. And then NQ hat sub B, how many people failed? Well, that would be 143 minus 46, so that would be 97, and that's at least 10. And then NP hat sub P, how many people who did the patch only quit smoking? Well, that's 30, and that's at least 10. And then 151 minus 30 is 121, so NQ hat sub P is 121, and that's at least 10. So with proportions, we need to check the success failure condition. NP and NQ must both be at least 10, and we had to check that for both samples. Now when you're doing this on your test, be very careful. You don't have P and Q. So if you're on the AP test and you put down NP sub B, you're going to get docked for it, because that's not NP sub B. It's NP hat sub B. This is the proportion from the sample. Okay? So make sure that you're using, you're using the right, the right symbols in this. Name the test. This is going to be a two-proportion hypothesis test. Now we need our test parameters and statistics. So for the support group, N sub P is 143. P hat sub P is 46 out of 143. And I'm just going to round that to, I want to round that, that's 0.322. And then Q hat sub P would be 1 minus 0.322, so that would be 0.678. And then N sub, I'm sorry, that's N sub B. And this would be N sub P, and that's 151. And then P hat sub B is 30 out of 151. And if I'm not mistaken, that is going to be around 20%, and that's 0.199. And Q hat, this is B up here, Q hat sub P is 0.801. Okay? Alright. So far so good. Now we got to obtain P. Now, we're using a normal model. So when we do a normal model for proportions, we do a Z, and for a one proportion test we said, okay, what is our observed value? Well, our observed value is P hat. What is the mean? Well, the mean is P. And how do we do the standard deviation? We do the square root of PQ over N. Okay. So now we're looking for the difference in the P hats. So on the top, here's what we're going to do. We're going to do P hat sub 1 minus P hat sub 2. That's going to be our observed difference. Minus, now we're going to see the observed difference in the P's. P sub 1 minus P sub 2. Now, let's notice something. When you go to your null hypothesis is going to be that P1 equals P2, or P sub whatever equals P sub whatever. So if they're equal, okay, if the expected difference in the P's is 0, okay, then this P1 minus P2 is always going to be 0 if your null hypothesis is P1 equals P2. Okay, so that's almost always going to be 0, unless there's a certain difference that we're looking for. And then we have to get the standard deviation of the differences. Well, what's the standard deviation of P hat sub 1 is the square root of PQ over N. P1 Q1 over N1. And the standard deviation of P hat sub 2 would be the square root of P2 Q2 over N2. Now, if I'm adding or subtracting two independent things, then what do? Well, I add the variances. So if this is the standard deviation, then I need the variance. Well, how do I get the variance from the standard deviation? I square it. So this is going to be P1 Q1 over N1, that's variance 1, plus variance 2. Then what do I do after I add the variances? I get the sum of the variances, then I take the square root. Well, now we got another problem. The other problem is we know p hat for both samples, we know q hat for both samples, but we don't know what p is. See, when we did a one proportion test, we said, oh, well, we think the proportion of brown M&Ms is 20%, so our null hypothesis was p equals 0.2. And then we said, okay, well, let's see if there's evidence that it's less than. So then our alternative would be p is less than 0.2. Okay. But in this case, they didn't give us p1 or p2. Okay. But what we do have to work from is we're going from the hypothesis that the two p's are equal. So we're going to estimate what those p's are. Okay, so if they're equal, they must be the same. Well, what do we have to go from? Well, we have this p-value and we have this p-value. So basically what we're going to do is we're going to use this information to estimate what we think these two p's are. And we're going to call that p pooled. Okay, now remember, when you're doing a sample distribution for a proportion, okay, if the p's are the same, and that means the q's would be the same, remember that the distribution, the variation in the distribution simply depends on the n size. So assuming that the n sizes are roughly the same, then the variation is going to be about the same as long as the sample sizes are roughly equal. Now in this case they are roughly equal. Not exactly equal, but roughly equal. So if these two p's are equal, then we would expect our variation to be about the same. So what we're going to do is p pooled simply equals the number of successes in the first sample plus the successes in the second sample over the number in the first sample plus the number in the second sample. So in this case we had 46 successes in the first group and 30 in the second, and we had 143 in the first group and 151 in the second. So that's 76 over 294, and that comes out to 0.259. Okay. So when we go over here, we're going to use p pooled wherever p is, because we're assuming that both proportions are equal. So in our problem, our first p is 0.322, our second p is 0.199. So that's the observed difference. Our expected difference is 0, because we hypothesize that two proportions are equal right there. And now we have to do the square root of p1. We'll use p pooled. So we'll do, by the way, q pooled here will simply equal 1 minus that. That would be 0.7741. Okay. So we're going to do 0.259 times 0.741 over our first sample size, which is 143, plus 0.259 over 0.741 times 0.741 over 151. So now we go to our calculator. Let's do all this math out. Let's see, we got 0.322 minus 0.199, and that's 0.123. And then we got to do 0.259 times 0.741 divided by 143 plus 0.259 times 0.741 divided by 151. And we get that, and then we got to take the square root of that. So the square root of that answer is 0.051. So what we're getting is a z-score of over 2 standard deviations away from our expected difference of 0. So that's 2.41. So what this would look like is, if I was to draw this out, here's our normal model of our difference in the two proportions. And here we have mu sub P1 minus mu sub P2, which I'm just going to call P1 and P2. We have in the middle P1 minus P2 equals 0. That's what we expected to happen. But then we had an observed difference, P hat sub 1 minus P hat sub 2 equaled 0.123. That's going to be over here somewhere. And that comes out to a z-score of 2.41, and we're going to shade that to the right. So then we say, okay, let's go to second distribution, norm CDF, and our lower bound is 0.123. Our upper bound is 1. Okay. Our expected difference in mu's is 0, and our standard deviation is 0.051. And if I do that out, I get a big P value of 0.008. So big P, P-val equals 0.008. Now, if our significance level is at the 0.05 level, then we're definitely going to reject it. Even if it was at the 0.01 level, we'd reject it. Okay. Now, when you do this, you got to put all this on your paper. This is on your AP formula sheet, by the way, so you don't have to memorize the formula. But the concept is simply you're adding the variance because you have two independent samples, and when you add the standard deviation of independent events, you have to add the variances. So that's all that this is on the bottom. Okay. So yeah, we got to put the formula down, but we can go and let the calculator calculate all this good stuff for us. So if we go to stat and test, and you go to 2-prop z-test, and the number of successes in sample 1 is 46, and the number is 143, and the successes in sample 2 is 30, and the number is 151. And our alternative hypothesis was greater than, okay, which we had right here. And we wrote that. There's our alternative hypothesis, greater than. So we're going to say let's draw this out, okay. And there it is, okay. Everything we got. So there's your z-score right there. There's your big p-value right there. So the calculator, again, we don't have to do all this right here, okay. We do have to write our calculation, but we then let the calculator do this piece right here. So we're going to make our decision. So assuming our significance levels at the 0.05 level, we are going to reject H sub O at the 0.05 level. Okay. So what's our conclusion in context? Well, if we rejected it, then the alternative hypothesis says that this group, there is evidence that the proportion of people who quit smoking in this group is higher than that group. Well, this group represents the group that did both. So we're going to put, there is strong evidence that the proportion of people, okay, now again we're inferring about all people who will quit smoking, is higher if they do the patch and counseling compared to the patch alone. Okay, so that's what our evidence is. So what does our p-value mean? Well, our p-value always means there is this probability right here of getting this value if this is true. Okay. Well, we know what the probability is. What is this value? That's the difference in the two proportions that we got. And what did we assume? Well, we assumed that there was no difference. So what this means is that there is a 0.008 chance of obtaining a difference in proportions of 0.123 if the difference in the proportions is 0. So assuming that the difference in the proportions is 0, the probability of us getting this difference in our two samples, it would be this, which is less than 1%. Now we got to do a 90% confidence interval. So remember, our confidence interval for a proportion, well, generally our confidence interval formula is statistic plus or minus margin of error, right? And then for a proportion, it was p hat plus or minus z times the square root of p hat q hat over n, because we never had p and q. We're trying to infer what we think p is, so we're creating an interval, so we don't assume we know what p is. But now we're doing the difference in the two p hats. So our confidence interval goes now to p hat sub 1 minus p hat sub 2. Our z-score is still the same. If it's a 95% confidence interval, it's 1.96. Right? Z equals 1.96. If it's a 90% confidence interval, then z equals 1.645. Okay? And that's different than that, then we got to find it. And then what we got to do is we now have to add the variances. Now, do we have to do p pooled? You might ask. Well, remember, when we do a confidence interval, we use the p hats. So we don't have to try to estimate what p is. We can use the p hats that we have. So we would, instead of, and we would still in effect be adding the variances, because the variance for the standard error for sample 1 is the square root of p hat sub 1 q hat sub 1 over n sub 1, and the standard error of sample 2 is p hat sub 2 q hat sub 2 over n sub 2. Remember, why do we not call this standard deviation? Because we're dealing with statistics, not dealing with the parameter. Okay, so then we would just add those. Okay, so now I got to get the variance from the standard error, so I wind up with p hat sub 1 q hat sub 1 over n1. All I did is square that, plus p hat sub 2 q hat sub 2 over n2. I added the variances, take the square root. It's the exact same concept that we did up here. The only difference is up here we did it with p and q. Down here we have to do it with p hat and q hat. So what we wind up with is the square root of p hat 1 q hat 1 over n1 plus p hat 2 q hat 2 over n2. So we already know that the difference in these two is 0.322 minus 0.199. Z-score for a 90% confidence interval is 1.645. And then we got to do the first sample was 0.322 for p hat. Q hat is 0.678, and n is 143, and 0.199, 0.801, and 151. Okay. Now we already know that that difference is 0.123, and we got to get this whole deal here. So we do 0.322 times 0.678 divided by 143 plus 0.199 times 0.801 divided by 151, and then we take the square root of that answer, and we get 0.0508. Okay, and then we got to multiply that times 1.645, and we get 0.084. So it's 0.123 plus or minus 0.084. So if you do 0.123 minus 0.084, you get 0.039, or roughly about 4%. And then if we do plus instead, we get 0.207. Okay, 207. So before I interpret that, how would you do that on the calculator? Stat test 2 prop z int. And there's sample 1. Now you got to know which one's sample 1, and then this one's sample 2. Okay, and then you calculate it, and there's everything that we got. Okay, we got 0.207 and 0.04. Okay, so now what we're doing here, what does this represent? Well, this represents the actual difference between p sub 1 and p sub 2. So that's why we created the interval. We use p hat sub 1 and p hat sub 2 to estimate the difference. So we are 90% confident that the proportion of people, okay, who will quit smoking is between 0.04 and 0.21 higher if they do the patch and counseling than the patch alone. Okay, so that's what this is about. This is about comparing the two proportions. So if you do the patch and the counseling, we're 90% confident that between 4% and about 21% more people will quit smoking than by doing the patch by itself. Okay, so that's the end of problem 1.